And part of our goal here at Yokogawa is to not only provide measurement solutions, but to provide education for you on power measurements. So our topic today, of course, is on the harmonic analysis of distorted waveforms. This is the second in our series of our webinar Wednesdays. A couple weeks ago, we did the fundamentals of electrical power measurement. Had a great turnout and a good audience, and had a lot of fun there. And so today, we're going to look at these distorted waveforms, measuring the power and doing the harmonic analysis on it. Then in a couple more weeks, November 12th, we're going to do our webinar on electric motor and drive testing. And that's always an interesting subject, a lot of distorted waveforms. And so this kind of leads up to that. So if you do have questions, please feel free to submit your questions, and we'll try to answer those at our website, Webinar Wednesdays at us.yokogawa.com. We've had some questions already submitted earlier, and we'll try to cover those in our presentation as we go along. Usually I let people know a little bit about Yokogawa history. It was founded in 1915, of course, in Japan, Tokyo, and they were the first to produce and sell electric meters in Japan. And our North American operations was established in 1957, and it started in New York State, and then we moved to Georgia in the early 80s. Our worldwide sales now are in excess of $4.3 billion. They operate 84 companies worldwide. Now, these are companies like Yokogawa Corporation of America here in Newnan, Georgia, and have over 20,000 employees worldwide and operate in 33 different countries. It was an AC voltmeter, about a 1930s vintage, pretty good accuracy, 0.2% accuracy class. It's a moving coil type, has the mirror scale and the pointer. Come a long way since then with our precision digitizing instruments that we have now. I always say that then there was as much work that went into that wood case on that voltmeter as it did into the movement and everything else, because it's a real classic type of an instrument. So, we've been in this business for quite a while to help you with your measurement solutions. This is our facility in Newnan, Georgia, where we have our test and measurement headquarters, and we do some manufacturing and all of our customer support here. So where's Newnan, Georgia? Well, we're just a little bit south and west of Atlanta, down Interstate 85, just far enough away from Atlanta, and close enough if we want to go into town. So that's where Newnan, Georgia's at. So today's topic is power measurement and the harmonic analysis on distorted waveforms. So our objective is to provide you with some tips and techniques for making these accurate power measurements on distorted waveforms, and a method for making and analyzing the harmonic content of various power waveforms. So that's what we're going to try to do today. First of all, why are we concerned with harmonics on the power system? Well, harmonics can cause a lot of trouble. They can cause excess heat in our electrical equipment, cause inefficient operation, wasted power, higher electrical cost, cause damage to the electrical equipment because of this heat. Some examples might include transformers can be less efficient. Circuit breakers and GFIs can trip. Electric motors can be less efficient. We'll talk about that. We can actually, because of the harmonics, get some reverse torque on these motors, and so they're less efficient. And in the power quality area, overheating in the neutral conductors in places like our offices and things like that. So what we plan to do is have a review of our basic power measurements. We covered a lot of that a couple weeks ago, but we need to review this just in case you weren't there. And so this is going to lead up to our measurements. And then we'll get into the power measurements on the distorted waveforms. Then we'll move into the harmonic analysis, some fundamentals of harmonics, measurement on these distorted waveforms, instrument considerations, especially in the current sensor area, and look at power factor on distorted waveforms. We'll look at a few harmonic analysis applications, some power and harmonic analysis on power supplies, electronic lighting load. Look a little bit on the variable speed PWM motor drive systems leading up to our next webinar, and look at a few of the power quality standards, an introduction to the IEC testing. These are quite involved, can be a whole topic just on themselves, but we will get into a little bit on those topics. And then answer your power measurement and harmonic questions. Hopefully we'll cover your questions, but again, remember, if you have questions, please get in touch with us, and that's what we're here to try to help you out. So let's get started with part one with our electrical power measurements on distorted waveforms. You know, our power companies generate nice, clean sine waves, but as soon as it gets out onto the line, gets into our buildings, they get all distorted and all messed up because of all the equipment that we have. So with our measurements, I like to always start with the basic of Ohm's law. We're talking about the power part of it right now. Okay, so the power, and typically the basic function, DC, is our volts times our current. That's our basis, our fundamentals for what we're doing in the power measurement part of it. And then, of course, there's the other parameters that you can use with Ohm's law, but we're going to be talking about basically the power, the voltage times the current. A couple things that we want to review, and we will use sometimes in our measurement, is the comparison between the average, the RMS, the peak-to-peak values, and this relates to a sine wave. Okay, so if we know the RMS value on a sine wave, we know that peak is square root of 2, 1.414. All right. Now, if we know the other function that we use quite a bit in some of our measurements is this average or half cycle average. And so if we have an average responding meter, like a lot of meters are just average responding, some mechanical meters, and they're average responding, and so we have a multiplier of 1.11, and on the mechanical type instruments, this was just a scale multiplier of 1.11. We do use it in some of the electronic instruments, to get that average to RMS value. So it does come up once in a while. And of course, we know our peak and our peak-to-peak values. Here's a display of one of our power analyzers. We hooked it up on a calibrator, and we had 120 volts RMS. This is what we call the mean value, that half cycle average, the mean value, scaled to RMS. So this does the half cycle mean average with the 1.11 multiplier, and basically it's 120 volts. And so our average, we went in and did the actual half cycle average or mean measurement at 108, and if you multiply that by 1.11, that should come out to 120. And then, of course, our peak on the sine wave should be, square root of 2 times that. So graphically, that's what we have. So, power measurement. First thing, what's a watt? Well, it's a unit of power equal to 1 joule of energy per second. Well, you look at that definition, you might say, well, Bill, I thought you were going to make this simple. I said, I'm not sure what a joule and all that stuff is. Well, that's the definition. Making it simple, if we have a DC source from Ohm's law, our watts is just simply the measured voltage times the measured current. Now, if we have an AC source, remember it's the measured voltage times measured current times power factor. Okay, and we don't want to forget that power factor component. So it's just not multiplying voltage and current. That'll give you volt amps, not watts. And I note that I say power factor not cosine of theta. A lot of our education, you know, we might have heard, well, volts times amps times cosine of theta, or the angle between the voltage and the current. We'll show you why that doesn't work, so that's why we refer to this as power factor. So our active power is typically defined as watts, RMS voltage times the RMS current times the power factor. This also may have, you may see the terms as true power or real power. Okay, all of these kind of the same thing. Then we have apparent power, which is our volt amps. We use the symbol S, that's a universal symbol used worldwide, and that's just the RMS voltage times the RMS current. How do we measure power? Well, on these distorted waveforms, all of our digital power analyzers are, you know, they're entirely electronic now that we're talking about, and we use some type of a digitizing technique. And so we have digitizers on both the voltage and the current waveforms. And then we use digital signal processing to determine from those digitized values the actual measurement values. Now, a lot of digital oscilloscopes will have a power measurement function, and they will use, to do a true power measurement, a special firmware inside to make these power measurements. So it's not just multiplying two channels together. You got to have a scope with the true power firmware in it. Now, anytime we digitize the waveform, you know, I say it is somewhat restricted because it is sampled data. So, you know, it's not continuous. There are holes in it. We've got to remember that it is sampled data. Now, most of our power analyzers and, you know, the scopes that we have today have an FFT, a fast Fourier transform algorithm, to do the additional power and harmonic analysis function. And so we'll get into that. But, you know, a lot of those have that as standard, sometimes as an option. So with the measurement of power, showing the formula, what we do is take the instantaneous voltage times that instantaneous current. These are the digitized values. Their voltage and current are sampled simultaneously, so we take all those instantaneous values of voltage times the instantaneous value of current, accumulate those in a working memory, and integrate those over some time period, okay, 0 to t, some time period, and then multiply by 1 over t. So it's the digitized value of voltage times the instantaneous digitized value of current, and then integrated over some time period. And this time period can be a variable. It's a front panel variable, usually on the front of our instruments, so it can be a variable. Here's an example. This is a power supply. Had a lot of noise on the current. Voltage was fairly clean. So if we look at the RMS voltage there, at 118.67 volts and a current of 0.6376, all right, we multiply those together, we get the VA 75.67. And then our power, our watts, is 73.07. And lambda is a universal symbol for power factor. So the power factor was 0.9657. So if we take the VA times the power factor, we should come out with the wattage there. And we're showing one additional function. We've got the frequency of the waveform, and we're showing, in this case, the current total harmonic distortion. So we can measure these simultaneously with the harmonics as well as all the true measurement functions, normal measurement functions. So it's just an example of some of our measurements. So true RMS measurements, again, the power is the instantaneous voltage times the instantaneous current, multiplied together, accumulated over some time period, multiplied by 1 over t. And we know the RMS, the root mean square function of voltage and current, where again we take the digitized value of voltage, accumulate them over some time period is squared, and then we integrate that, take square root, well, multiply by 1 over t and take the square root of it. So that's your formula for RMS, root mean square. Now these calculations provide a true power measurement and a true RMS measurement, and it is done on any type of a waveform. It includes all the harmonic content up to the bandwidth of the instrument. So when we get a distorted waveform, these algorithms will give us the true power and the true RMS measurement, regardless of what we have, but it is up to the bandwidth of the instrument. So let's look at a quick single-phase measurement. We've got some type of a load here. We've got an AC source out here. We put our wattmeter in line. We measure the current in series and the voltage from line to line. You'll notice there are some showing the polarities. These are instantaneous polarities. Very important that you follow the manufacturer's wiring diagram and these polarities for the instrument. If you get some of these turned around, you may get a negative power reading, and that's not going to be correct. So make sure you follow whatever the manufacturer's wiring diagram is, and how they indicate those. So on a single phase 2-wire system, very simple. The wattmeter just shows the the power that's dissipated by that load. We measure the voltage and the current applied directly to the load, and then that power measurement is actually that being dissipated by the load. Power factor measurement on a distorted waveform. I said earlier that we have to look at power factor, not cosine of theta. We're taught that a lot in school to begin with, and that's fine if you work at the power utility or clean sine waves, but most of our work is not that type of work anymore, is it? So how do we accurately measure, if we were trying to do a phase angle on this, a time, we got to pick some type of a zero crossing. And so where's a common zero crossing? Well, you might say it could be at the peak, but very difficult to determine that exact peak. You might take maybe on this current, maybe halfway in between, the rising and falling edge here, and then the difference between that and the voltage crossing. A lot of different ways. I don't think we would ever agree on where the true, zero crossing might be. So very, very difficult to do it. So going back to some of our power basics again, what we call the power triangle, the phasor diagram. We draw the watt vector as the base of the triangle. And in this case, we're showing VAR as vertical because it's an inductive circuit, and by convention, for an inductive circuit, we put VARs going upwards. If it was capacitive, they would be drawn downwards. And then our volt amps, just the VA part of it, is the hypotenuse. So from this, our true power factor now is watts divided by volt amps, base divided by the hypotenuse. And this is true power factor. So for a sine wave only, we can use power factor equal to cosine of theta, and we can get a good zero crossing and measure that time and get the angle. This is what is defined as displacement power factor. But for all other waveforms and what we typically deal with in our day-to-day work, we don't have nice clean sine waves, and so that's where we do the watts divided by VA, and this is defined as true power factor. So regardless of what the waveforms look like, you saw how we calculate the watts and the VA. Doesn't make any difference. These are true measurement values. So this is the true power factor. When we're dealing with distorted waveforms, instrument bandwidth is very important consideration. Here's a couple examples. Look at this RMS current right here, and this one was had a channel 1 had a 2 megahertz bandwidth. Okay, you can see that the waveform, we can see all the little glitches and everything in it, and the current was measured 0.1397 amps. Over here, the instrument bandwidth was limited to only 500 kilohertz. You can see a lot of those, parts are filtered out, smoothed out, and so we're not seeing the same thing. And so our current is measured as 0.1244. There's difference, and that's due to the bandwidth of the instrument. Big difference here when we calculate the power factor. Okay, so you can see what happens. We got to take the instrument bandwidth into consideration when we're dealing with distorted waveforms in order to get all the harmonics. So using a different type of an instrument can result in different types of measurements. So we talk about current sensors. This is very important. Generally, we can take in the voltage direct up to 1,000 volts, so that's pretty much defined by the instrument specifications and the bandwidth. But the current sensors, we can't bring in maybe all the high current, so we got to go through some type of a current sensor. So these are very important to consider in your measurements. Some of the shunts. Now these are good for DC. It's just a precision resistance that we're putting in line. So those are DC, not good for distorted waveforms and high harmonic content. We do make some of our own brand of potential and current transformers. These are good up to about 1,500 amps and about 3,000 hertz. And down on the low end about 30 hertz. Scope probes. Now, scope probes have a good bandwidth, and sometimes we like to use them, but you have to be careful using them on a power meter with the match of the instrumentation with the probe. We do work as a reseller from the AEMC, and they have some very good clamp-ons with some good bandwidth that we have selected as products that would be good for power measurement. And then Pearson Electronics, very popular in the lighting industry. They have good high bandwidth and medium accuracy. And then this is a system that we developed with Yokogawa and Lam. Used to be Dan Physic. Maybe some of you are familiar with that. This is a very specialized DC to high frequency current transformer. It is an active type, so it has a power supply signal conditioning unit with it. And these will go up into the hundreds of kilohertz and very accurately make current measurements like a 0.05 to 0.02% of full scale. So it's another good solution for your current measurements. So some selection considerations. Accuracy is typically defined as the CT turns ratio on the CT itself. Phase shift is very important because we're measuring power. And phase shift represents a part of the the power factor is a phase shift. So what's acceptable to you and your application? Say if we had 1 or 2 degrees, cosine of 2 degrees, be another multiplier 0.9994. Sometimes that's okay, sometimes it's not. So you got to look at that and consider your application. Frequency range is very important when we're talking about distorted waveforms. And shunts, that's why I say these are, good to, line frequency, a few hundred hertz. Typically, be careful on any type of distorted, waveform. Then we have the Hall effect type CTs, transformers, that will measure DC and AC. With the Hall effect device, you do lose some accuracy just because of the technology. And the active type, like the Yokogawa Lam CT, very accurate and very good for distorted waveforms. And then your standard instrument transformers. These are good typically from about 30 hertz and higher, like ours, from about 30 hertz to 3,000 hertz. There's various types of these instrument transformers around, but look at their specs very carefully. And some will work, and the others you have to be careful of. Other selection considerations, of course, is the output. We've got to match it to a measuring instrument. So some of these have a millivolt per amp or a milliamp per amp output, or just like our instrument transformers typically have like a 0 to 5 amp output. the impedance, the load, or the burden that's put on the CT from the instrument is also very important. This is what I was talking about, scope probes. Use on scopes, but be careful hooking up a scope probe to a power analyzer, because a lot of those scope probes are meant to match the input circuit of a scope, different type of input impedance, and we have a high input impedance typically on the power analyzer. So just be careful, in how those are used. Then, of course, how are you going to use it? The physical requirements, size can be a factor sometimes. Do you need a clamp on, or can you use a donut type, feed the cables through the donut hole? The other thing to consider is that distance from the load to the instrument. And this can be a burden on the CT. If you've got questions, we can always help you, with that selection. Here's a word of caution. Never open circuit the secondary side of a current transformer while it's energized. A CT is a current source. So by Ohm's law, E equals IR. This is internally. What happens when R goes very large, or if we open circuit it? E becomes very high, and this is the internal voltage that's generated inside that CT. So with that high voltage generated inside, it can cause magnetic saturation of the core, actually burn the windings, damage it, could just totally destroy the CT. So it's a very dangerous situation. So always de-energize the current going through the CT before you disconnect it. Okay, let's look at harmonic analysis now. So the distortion of an AC waveform can take various forms. Could be unbalanced polyphase wave shapes, where the phases do not have the same magnitudes, or the phases are not typically balanced 120 degrees apart. Or more often, the wave shapes are not ideal sinusoids. This is what we're concerned with right now today, non-sinusoidal waveforms. Many causes. What causes these good waveforms that we get from the power utility to get all distorted? Well, a lot of our circuitry that we use, the nonlinear magnetic circuits, in our devices, things like rectifiers, capacitors interacting with our inductors, switching power electronic loads, phase control rectifiers, AC voltage rectifiers, and our inverters, electronic ballast, all these types of devices and many more, just cause distortion on these waveforms. So here's what we'll talk about, a non-sinusoidal waveform. And this could represent a current waveform versus time. So we don't have our nice clean sine wave, we got something that's all distorted. So if we break this down and analyze it, the distorted waveform is made up of various waveforms, various amplitudes, okay, various frequencies, okay, if we look at this in the frequency domain, and different phases. And probably can't see too much of a phase shift here, but those three parameters is what, if we break down that waveform and look at individual waveforms, all these would add up together to give you this resultant distorted waveform. So in the time domain, this is our result, and then we can break it down in the frequency domain of various sine waves, of various amplitudes, frequencies, and phase. So harmonics then, are defined as voltages or currents or power at frequencies that are some multiple of the fundamental frequency. So as an example, for a 60 hertz fundamental, we could have harmonic frequencies in a simple format of 120, 180, 240, and so on. Then our harmonics are usually defined, as specified as orders, right? So our 60 hertz fundamental, our third order would be 180 hertz. So 60 times 3 is 180 hertz. Then we refer to our harmonics as even order and odd order. And then some complex waveforms can have what we call interharmonics or non-integer orders. So instead of a third order, we might have one at 2.7 or something odd like that. So that would be a very distorted waveform, but there can be other interharmonics that might be on that waveform. So remember how we calculate power. We digitize that incoming voltage and incoming current. We're going to repeat this so you know what we're doing. And we take the instantaneous voltage times that instantaneous current. We accumulate them over a time period, integrate that, multiply by 1 over T. And so we got a true power measurement regardless of the wave shape. And so the RMS values of the distorted waveforms, calculated as the sum of the harmonics, okay? This is showing the integer harmonics. More precisely, it's the DC component plus the summation of all the harmonic orders. Then power of the distorted waveform is calculated, same way. We look at our DC power, the DC voltage times the DC current, plus, now these are all sine waves, the fundamental voltage times fundamental current times phase shift between voltage and current on that fundamental, and so on. Okay, and we add all those up together. And more precisely, instead of the integer harmonics, we can go from the minimum order to the maximum order of each of those harmonic contents that are there. So remember, these algorithms that we use in the calculation give us a true power measurement and a true RMS measurement. And the key thing is up to the bandwidth of the instrument. So in our harmonic analysis, well, the approach we use is to, we got to get the frequency domain information. And we use the good old Fourier analysis technique. You may have had some of that in school. Hope you never see it again. And we got all these nice digitizers and DSPs and everything that do it for us now. And so we do the Fourier analysis. When the waveform's digitized, we get a basic discrete Fourier transform, what they call a DFT. And then in our instruments, we use the fast Fourier transform, the FFT, to get the harmonic data. So in our instruments, we use the FFT. You get a quick display, it's accurate. You can use the discrete Fourier transform in some instruments. It's a little bit slower. We'll give the results a little bit different, but in our instruments, we use the FFT. So again, we use the FFT algorithm. And on the FFT, this is very important. The analysis must be performed on a periodic waveform with a true integer number of cycles. And this is very important. And to do that, in our power analyzers, we use a phase lock loop tuning circuit. You'll see PLL, phase lock loop. It's a digitizing digital tuning circuit like you might have on our TVs and radios and things like that. And it syncs on the fundamental, and it adjusts the sample rate internally so that we get a true integer number of cycles to do this FFT calculation on. So that's very important. Some other things on our FFTs, the window function we typically use is rectangular. It's a 32-bit processing, and depending on the instrument, the FFT data length can be from 1,024 points on some of our entry-level products up to 9,000 points on some of the high-end products. And so the sample rate is that we're using is variable. It's a function of the fundamental frequency, and it's set automatically by the PLL circuit. And our frequency resolution then can be calculated as the sample rate divided by the points in the FFT. Here's a simple math FFT analysis function. This might be something like if you use your scope. And I'm not downgrading scopes at all. This is actually done as an FFT math function in a power analyzer. But this is a simple math FFT. And if you look at this, you'll see all this noise floor. This is what they call false harmonics or bleed. They're due to the point that this is not a true integer number of cycles. And so the simple FFT just takes all this data, calculates point by point, and we have an odd number of samples, and it looks at that, maybe that last half cycle or partial cycle, and it looks at that and it gets confused. It thinks it's harmonics, and that's what's reported down here. Now, if we're measuring up here in the the amplitude on these high harmonics, we can measure those just fine with our scope or this simple math function. But if we're trying to do a total harmonic distortion, which includes all these harmonics, it's going to be difficult to do. Yeah, they're going to be able to do it very good with all this false harmonics or bleed down here. So here's the analysis on the same waveform. This is done in the power analyzer, where we phase lock loop, get the fundamental, and we get a true integer number of waveforms. And I'm not sure where this starts, but it determines it all internally in the DSPs, and so we have a true integer number of cycles, and that we do the math calculation on. Now we got a clean, waveform. We can measure all these amplitudes, and you can see some of the odds and evens, harmonics, all the way across, very clear. Okay, let's look at a couple of applications. Here's a power supply input. We kind of saw this waveform earlier, and so we got a sine wave, or a little distorted sine wave for the voltage, and this is the current. And when it capacity type, it turns on at the peak of the voltage. So really, a lot of distortion between those two waveforms. So we look at typical data, might be the RMS value of voltage and current. We got the true power measurement. We got the power factor. Remember how power factor was calculated? Watts divided by VA. So here's your watts divided by the VA. If you got a calculator, you want to check that real quick, but that looks about right, doesn't it? This is the VAR, our frequency. And this was a crest factor. This is a measurement that we can do, and the crest factor can be important in some of our digital instruments and some of our products. It's the ratio of the peak divided by the RMS. So this is the crest factor of that current waveform that we saw. If we look at the harmonic display, the harmonic spectrum of this, you'll see our voltage, and put the cursors on here, make a couple cursor measurements on the, we did this on the fundamental. Okay, down here, it's where it shows the order with the plus sign. So that's order 1, and then the X is the 5th order. Okay, so we can look at the amplitude on each one of these, harmonic orders pretty easy. And we can see the power. All right, look, we've got a lot of harmonics out here in the current side. Decays pretty evenly, doesn't it? And then we've got voltage that, drops off pretty quick. This is very low. This is a log scale in amplitude, so this voltage is very, very small. And so some of these power harmonics just don't even show up because of that low voltage. And so we can see we got a good measurement in the fundamental, and still some good power measurement at the 5th order. And the rest of them drop off pretty quick. They're gone. They don't even show up. Now, there's a couple reasons, because one of them could be amplitude. The other is what we cannot see, and that's the phase. These can be out of phase, and voltage and current actually cancel each other, so there is no power measurement. So if we look at our same old power supply, Here we're looking at the RMS value, and 4 is just happen to be what channel it's on, so don't get confused with that, but it's the RMS voltage. Here's the DC voltage component. Okay, there was no DC on this particular waveform. And then we can go in and break it down to the harmonic order, and this breaks it down to order number 1. So this is the true RMS value. Includes all the harmonics that are available to measure with that RMS calculation formula that we use. True RMS measurement. This is just the fundamental. And then this is the current RMS value of the current, 504 milliamps. And you can see we do have some DC current available. And with the harmonic analysis, we can get that by looking at the order. So order 0 is what we define as the DC value. Order 1 would be the fundamental. And so we're looking at, in this case, order 0 for the DC value. Here's the fundamental current. Remember, the RMS current is 504, and the fundamental was 488. This is our true power measurement. We had 57.28 watts, and no DC watts. Is that correct? Should be, because we don't have any DC voltage, even though we got DC current. So there's no DC power. We give you a lot of different displays for analyzing the data. Here we can list all the harmonic orders, and this can go out to a couple of pages to get them all. This page shows out to 22 orders, and we're displaying right now the voltage and the what we call harmonic distortion factor, and that's the percent of the fundamental. Okay, so this first order, 116.62, is 99.93% of that fundamental. Okay, so it's percent of fundamental is a harmonic distortion factor. So we can go through and look at the 22 orders of that, and here's the current over here. So we looked at the voltage and the current, and just a list of data for you. Then we can break this down a little bit more. Here I put in the power measurement, and you can see how this kind of goes away. So, some of them are negative. That's because we lost our voltage and current. Reference are not always there. Even though we got current that goes out pretty high, we lose the power because the voltage harmonics were not there. We can look at the phase of each one of these harmonic components. And this could be helpful if we're trying to put in some filters to clean things up. You'll know the amplitude, you'll know the frequency, you'll know the phase between the voltage and the current. So if you're doing your filter design, hopefully this information will give you the information you need to design maybe an RLC filter to block some of these harmonics. So here's our power factor measurement again, and I'll make sure we understand this. We do a true power factor measurement of watts divided by VA. So here's our watts, 72.03. Here's our VA, 99.78. So it's the watts divided by the VA gives us the 0.7219 as our power factor. If we look at the power factor on a sine wave, and this is a vector analysis done from one of our power analyzers, and we look at the phase angle between the voltage and the current at 20.64 degrees. So if we take cosine of 20.64, down here we get 0.9358. Now, if we take watts divided by VA, so our wattage over here was measured at the 70.24, and the VA at the 75 0.06, so we get these measurements over here. Okay, so watts divided by VA comes out exactly the same. Now this is on a sine wave. So true power factor and displacement power factor on a sine wave obviously got to come out the same, and this just shows you how they do that. Here's another example. This is an old type of a compact fluorescent lamp. I like to keep it around because it's got so much noise and distortion to it. So if any of you guys are in the lighting industry, don't get too upset because you know, they're a lot better now. But this is an old one, and had a lot of distortion on that current. And so, you know, we look at that as an example. Same thing, we had, you know, our power is measured as 13 watts and VA at 20.7, and had the VAR, and the power factor at 0.633. And a lot of distortion on that current, and that turn on here distorts the voltage a little bit. So here's our harmonic spectrum of the voltage and the current. Again, you'll see that current goes way out in the harmonics, but the voltage drops off pretty quick, so we're not going to have much harmonic power. And again, I set the cursors just at the first and the fifth because I had my first fundamental right here. Third, the fifth was kind of high, so that's why I chose that one. So here we can look at the power, and this is what I was saying. The power harmonics go away, and it's very hard to see, but there's a little red blip right down here at the bottom, about the third order. That shows a negative power. So we actually have because of the harmonic phasing, actually have a harmonic that's going in the reverse direction on that lamp. So those are things that we can see. So if we look at our harmonic analysis and we measure the THD, total harmonic distortion. Okay, so we want to set the harmonic orders typically from the fundamental to the maximum order, which on this instrument was 500. And remember, the harmonic distortion, THD, is the square root of the sum of the squares of each of the harmonic components, and then we divide by, in this case, the total RMS value of the current. Okay, two ways of doing it: divide by the total, or divide by the fundamental. And so these two examples, we have both calculation methods available to you. So typically our UL and CSA method like to divide by the total RMS value. The IEC method defines it as dividing it by the fundamental. So we give you both methods. It's a math, so they will be different. The total value is going to be higher in many cases than the fundamental. So we're going to divide by a higher number, and so it could give you a lower reading just because of the way we do the math on the THD, which is correct. Well, you got to remember, it's just a math reference. But we give you both methods to be able to calculate. Here's a little bit of information to look at on a PWM motor drive. Here's our pulse width modulated voltage, where we chop the voltage, okay, and then we vary this frequency in here. So it's a very distorted waveform, and we get a lot of switching noise over on the current side because of the PWM up here on the voltage. So here we're looking at the total power, total VA, and the total power factor. We can look at the VAR, and we had the drive running kind of slow at 27, 28 hertz. And look at the peak, the RMS value. And here's where we use the mean value. And this mean value could be the fundamental voltage. And that's why I brought that up earlier. because this mean value is quite important a lot of times in our drive work as the fundamental, and that's what really relates to the torque of the motor. Now this is where we talked about the bandwidth of the instrument. Here's one where we had the bandwidth capability out to 2 megahertz. And look at that RMS voltage up here on this PWM, 149. Now here we're in the harmonic mode. And in the harmonic mode, it was limited to 500 orders, or in this case, 30 kilohertz. So we're only being able to look at this voltage over 30 kilohertz. And you'll see we select the harmonic order, the starting and ending, and it ended at 500 orders. And you'll see this does not say RMS; it just says U for voltage. So it's not a true RMS measurement. So you got to understand how your instruments are working. So measurements made in the harmonic mode can be bandwidth limited, and you just saw that. So some of the voltages and currents compared to the normal RMS mode could be different. So in the harmonic mode, it's only calculated to the maximum harmonic order that the instrument can handle. So our harmonic calculations, remember, in the true RMS mode, we've gone through this a couple times, okay? And then in the harmonics mode, it's not a true RMS measurement. It's only from the minimum to the maximum harmonic order that are set. So this could be the minimum at 0 up to the example I just had was 500 orders. But that instrument had a 2 megahertz bandwidth, but this only gave us 30 kilohertz of bandwidth. So again, things to think about and understand how your instruments are working. So other instrument considerations, some of our instruments, some of these instruments have 100 kilohertz bandwidth, and say if we were looking at a 60 hertz fundamental, we can get 50 orders with that harmonic analysis off of these instruments, which is a 3,000 hertz bandwidth. With the WT1800, it has a 1 megahertz analog bandwidth, but we do harmonics 500 orders, so from our 60 hertz, that's only 6,000 hertz. One of our real high frequency instruments with the PX8000 has a 20 megahertz voltage bandwidth. We can do 500 orders, but again, that's only 30,000 hertz compared to 20 megahertz. So you can see the difference in measurements. And a scope. Scopes are interesting. Here's one of our 500 megahertz scopes that has a harmonic analysis function, but the harmonic analysis function was designed to meet the IEC 61000-3-2 requirements, which says we only need to look at 40 orders. So from our 60 hertz fundamental, that's 2400 hertz. So I got a 500 megahertz measurement out here, but only 2400 hertz in the harmonic mode. So that's what's happening with your instruments, and so please, look at your specs and understand how the instrument is operating. Sometimes some of our applications require maybe doing harmonic analysis on 2 different frequency sources, such as an input and an output. And our newer instruments, we can perform the harmonic analysis simultaneously with the standard power measurements. So here's a dual harmonic application. As an example, we could look at the output of a drive and look at the input to the inverter drive or power supply. So we've got a clean sine wave input before it's all chopped up. This is the power supply current input that's pulsed. It turns on at the peak of the voltage, so we get that peak, pulse current. A lot of difference between the two of them. So we can look simultaneously between these two waveforms. So in our dual harmonics, this would be the power supply input to the drive, and a lot of harmonic content on the current side, and the voltage drops off pretty quick, not too much. But then when we look at that PWM output, we know we have a tremendous amount of harmonic content on the voltage side. And you'll see kind of some beat frequencies in there. Then the current is pretty much right there in the fundamental. So even though we have a lot of high harmonic content, where's all the power? Power is right here in the fundamental. Here's some examples of our dual harmonic analysis. We look at the two frequencies. This is almost 60 hertz and 20 hertz on the drive. And we can look at the total harmonic distortion of the voltage and the current. And here is the total harmonic distortion of that PWM voltage and THD of the current. So we get all these simultaneously, input and output together. There's a lot of different power quality standards, and it'd be difficult to go through all of them in detail, and not going to be able to do that, but some of them just to refer to, need to really dig into those and understand them. But our IEEE 519, the IEC requirements of IEC 61000 has to do with a lot of our, home appliances and things like that, and it does have some interesting requirements of doing interharmonics. So we do have a product that will do those interharmonics. And so with IEC testing, you can do a full compliance test, and here you got to use the latest equipment, software, and everything to do that requirement. Now you can do what they call a pre-compliant test, where you could use a basic instrument for the harmonic analysis and get a good idea of your product design before you send it off to a full compliant test lab. So in the IEC 61000, they break it up into different classes of products, and each product has a different harmonic analysis pass-fail. And these interharmonics are interesting the way the IEC has defined them. So it is looking for harmonics other than just the fundamentals or the integer, like the second, third, fifth. Okay, it looks at the ones in between. And it breaks it down into some what they call grouping. So you can have to calculate the amplitude in these various groups. So it's a complicated measurement, and we do have one of our products that will do this IEC compliant testing. If we get into some questions, we can try to help you on that. Then we get into part of the grouping and the subgroups, where we look at an integer value and look at a one harmonic, subharmonic on each side. So again, we're talking about the grouping of the IEC measurements. And this is just so you'll, if you hadn't heard of it, you'll have an idea of what these are. So again, some other ideas on the grouping and the various frequencies that they combine together to calculate the THD. Another one that's pretty popular is the IEC 62301. This is like our household equipment. Okay, the power quality, the standby power, and the instrumentation or the measurements that go into all that. And there's it specifies the methods of making these measurements so that we're all making the measurements the same way. And most of it has to do with some type of electrical household appliances. So the main objective is that we're making the measurements the same way, and we look at the standby power, we look at the harmonic content, and we do it all the same way. And this standard, the last time I counted it, breaks down to 25 various household appliances. And part of that is that it does have to do with the THD, so we've got to measure total harmonic distortion, as well as the real power and some of the other appropriate measurements. And in North America, Energy Star standard is typically used for this. So Energy Star goes along with IEC 62301. So if you're doing Energy Star compliance testing, it agrees with IEC 62301. And so there's a test report that can be generated from our test software, and you identify the appliance, the test equipment used, limits, measured data, all that's in the test report. And it does require the harmonics testing. A lot of other harmonic standards, such as Navy has a MIL standard, 1399, Air Force is a 704. The DO 160 for commercial aircraft, they have theirs, and there's other that we see as industry or product specific, harmonic standards. So generally, the instrumentation will deal with most of these measurements. So in conclusion, just to wrap up a little bit about what we did, gave you a quick review of some basic power measurements and, on how we do this on distorted waveforms. How we do the power measurements, how we do the power factor measurements is very important. Then we looked at the harmonic analysis, fundamentals of harmonics, looked at the measurements of distorted waveforms, instrument considerations, and especially current sensors. The power factor, how do we calculate power factor on those distorted waveforms? Gave you a few practical examples on a power supply, a lighting load, and a PWM motor drive. And a quick review of these power quality standards. And say if you get into certain these standards and things like that, we can try to help you out with the measurements, but generally we can do it. And so hopefully we have answered your questions on the harmonic analysis. So, Yokogawa, we've got a complete line of power analyzers to meet your application and your budget. We have the support from our field sales reps. We have internal application engineers here in Noonan, Georgia, and all to help you out with your questions. So don't hesitate to give us a call if you do have a question. And, with our instruments, we provide a guaranteed measurement accuracy over the bandwidth of the instrument. We do have available NIST calibration as well as ISO 17025 calibration, all done from our factory here in Noonan, Georgia. And all of our power analyzers do have a 3-year warranty. So just a couple of the products, a little commercial there. And so we have scopes with power analysis functions. And as I mentioned, we have a lot of webinars. So if you're looking for webinars, it is on our website at tmi.yokogawa.com. Write that down and go to our technical library and look at webinars on demand. And if you do want a copy of these PowerPoint slides, they will be posted on the website a little bit later. So, our webinar Wednesdays was a 3-part series. We have done our basic power measurements back in October 15th. We got our harmonics done today, and in a couple of weeks we're going to do motor analysis. We also have, webinars apparently on the oscilloscopes and different applications, and so you can register right there. And some upcoming events coming up here in next January. There's the Motors and Drives Conference, a nice place to be in Orlando, Florida, and mid-January. Then we'll be at APEC, Applied Power Electronics Conference. It's going to be in Charlotte, North Carolina, in mid-March. So we'll be at those events also. Hopefully you can attend, and be glad to see you there. Here's a little homework assignment. We'll have a little bit of fun just before we close. We've got a motor seminar coming up. Even if you're not involved with motors, this is fun to do. Count the number of electric motors in your house. And just some tips where to start. Look in your kitchen appliances, your heating and air conditioning system, your home entertainment systems, equipment in your home office, lawn equipment, electric lawn equipment, others. So, it's fun to do. See how many you can count. And if you're going to be with us in the Motors webinar, we'll check with you and see how many you did. So have some fun with this. And thank you for attending. I'm going to give it to Christina to wrap up.
Thank you, Bill, for a wonderful presentation. We have unfortunately run out of time for our Q&A section, but please be assured that if you did submit questions, they will be answered via email. Remember, you can always reach us at Webinar Wednesdays at us.yokogawa.com. Also, within 48 hours of this presentation, please visit tmi.yokogawa.com under the Events tab to download the full PDF. With that, I'd like to once again thank you all for attending and participating in this online web seminar. Thank you, and we hope to see you at our future seminars.